In this clip, we're going to explore the patterns that set up when we set up these drug calculations as proportional rates using a table like we did in the clip for example 1b. What you'll have by the end of this little clip is a pretty much surefire way of setting out and solving all of the problems that you'll need to do for your calculations for this course. More importantly, you'll have a way of checking the reasonableness, confirming the reasonableness of your answer, and a way to check your final answer so that you can be absolutely confident that you are administering the right amount of medication from your calculation. So let's start with a drug that comes in a suspended form. It contains 5 milligrams in every 2 milliliters. And we'll just play with those units, lay it out in a table so that we can make sense of the numbers, and look at some patterns that happen when we take more or less of the suspension. The units that we're working with here are milligrams and milliliters, so we get those into the box first so that we get the numbers in the right row. Now let's make a couple of columns here. I'm going to put the 5 milligrams here and the 2 milliliters here. So we've got 5 milligrams per 2 milliliters, and then if we just extend that table out, we can go in either direction. If I pour out 1 milliliter of the drug, I'm going to end up with 2.5 milligrams, 2.5. And if I pour out, say, 4 milliliters of the drug, I'm going to end up with 10 milligrams because I've doubled the volume. I'm going to also double the milligrams within that volume. Okay, so that was the same thing that we talked about in that last clip about the proportionality of these rates, and keeping in mind what you're physically doing when you're thinking about these problems. So now when we analyze this table, there's proportionalities in every direction in this table. The milligrams are always 2.5 times the number of mils. So in other words, 5 is 2.5 times 2, 2.5 is 2.5 times 1, 10 is 2.5 times bigger than 4. Okay, we've already talked about the relationship going horizontally, so 5 is twice as big as 2.5, just as 2 is twice as big as 1. And same going here, the 4 is twice as big as 2, 10 is twice as big as 5, so there's a relationship vertically, there's a relationship horizontally, and there is also always a relationship diagonally. If you notice here, 2 times 10 is 20, and that is the same as 5 times 4. 1 times 10 is 10. That's the same as 2.5 times 4. So it's the product on that diagonal, if we multiply those two numbers together, will match the product of the matching diagonal. Okay, that happens anywhere in the table. That's going to be really useful when we set up these problems for the drug calculations. Okay, now let's look at this drug, use it within a typical drug calculation. So we've got our drug that comes in a suspension containing 5 milligrams per 2 mils. This time our client requires 15 milligrams, and we want to know how many milliliters we should administer in order to get that 15 milligrams. So again, we set up our table so that we've got milligrams and milliliters are the units that we're working with. We are starting out with 5 milligrams in every 2 milliliters. And in this case, we want 15 milligrams. And the question is, how many milliliters will I need to get those 15 milligrams of medication? Now I hope that you can see, without turning on your calculator, that 15 milligrams is 3 times bigger than the 5 milligrams that we've got in 2 mils. So you should hopefully see that we need 3 times more volume. So we are going to need 6 milliliters of the suspension in order to get 15 milligrams of the active ingredient. So that's a nice straightforward one, but I want to look at a couple other ways of getting the answer so that we get the process down. So when the numbers aren't quite so friendly as this one, we've got a process for getting the right answer. So let's first check our answer. If I put a 6 in here, which is 2 times 3, then when I look at the products of the diagonals, they should, if my answer is right, then 2 times 15, which is 30, should be the same as 5 times 6, that's 30, so I'm confident that 6 milliliters is the correct answer. Now let's go back and see if we can find a way to use that, what we know about the diagonals, to find another strategy for working out the unknown value when they're not quite so straightforward. So I've put the table back here again. We've got 5 milligrams per 2 mils, and I want 15 milligrams. So we know that the diagonals, 2 times 15 is 30, and I know that whatever this unknown value is, that times 5 also has to be equal to 30. So what I'm asking is 5 times what is equal to 2 times 15? In other words, 30 is how many times greater than 5, and that is a division problem. Okay, so if I multiply diagonals, 2 times 15, and then divide by the number that's diagonally opposite the unknown value that I'm looking for, so I'm dividing by 5 this time. In other words, I'm saying 5 times what is equal to 2 times 15. Then I get that magic number 6 again. Okay, so the pattern is, no matter where in the box the unknown quantity is, you can find that quantity if you multiply the two numbers that are diagonally opposite and divide by the third number, which is diagonally opposite your unknown value. Okay, so always in these problems there will be 3 known values and 1 unknown value. It doesn't matter where the unknown value is. If you multiply the diagonally opposite numbers and divide by the third number, you'll find that unknown value. Now let's look at just a slight variation on this problem. I've still got a drug that comes as 5 milligrams per 2 milliliters, so I can put my 5 in here and my 2 milliliters in here. This time I want to know how much to administer in order to get 12 milligrams. Okay, so this time my unknown is still down here in this box. That's my question mark. Using my common sense and looking for reasonableness, 12 is a little bit more than 2 times bigger than 5. So this 12 that I'm looking for, 2 times 5 would give me 10 milligrams, so if I poured out 4 milliliters, I'd get 10 milligrams, so I'm going to need a little bit more than 4 milliliters. 3 times 5 would give me 15, 3 times 2 would give me 6, so I'm looking for something between 4 and 6 milliliters for my answer. So let's use the diagonal operation to work out our answer. So the value that we're looking for is down in this spot. There are 2 numbers diagonally opposite here, 2 times 12. So if to find my question mark value, I'm going to multiply 2 times 12 and divide by the 5, which is the number that's left over, the number that's opposite what I'm looking for, diagonally opposite. So my answer is going to be 24 divided by 5. And 24 divided by 5 is 4.8. Okay. My unknown value is in the milliliter row, so I know that my units are milliliters. That's another good thing about this box, is it helps you keep track of the units that you're talking about. That's good for my estimate, because I said it was going to be a little bit less than 6 mils. It was going to be between 4 and 6 mils, so we've got that covered. I can do a check. If I put my 4.8 in this box, then my check is going to be, does 2 times 12 equal 5 times 4.8? So 2 times 12 is 24, 5 times 4.8 is also 24, so I'm confident that my answer is correct. If I were going to do this problem using the formula, then my thinking would be something like this. I've still got a 5 milligrams per 2 mils to start in my box. I want 12 milligrams. Okay, so for the formula, I need to think about what it is I want and what it is that I have. Okay, so the formula says find out how many times bigger what you want is than what you have. So we go 12 divided by 5 and multiply that times the volume. Okay, and can you see that in actual fact that's the same calculation, we just get to it with slightly different thinking. We've got 12 divided by 5 times 2, just like we did over here. And so our answer is naturally going to be the same number, 4.8 milliliters. Okay, and again, if I put my 4.8 up in here in my box, then I can do my diagonal check. 2 times 12 is 24, 5 times 4.8 is 24. So I'm confident with my answer, 4.8.